Okay, I'm going to start because 50 minutes is really short. So thanks everybody for joining today. And feel free to keep the chat active. Trip is here. She'll let me know if I can't see. So just a really quick recap. We were covering hyperplanes. Oh. Here, right? Share screen, advanced, right? All right. So we were talking about hyperplanes and to separate two classes of objects. We talked about dot product that you learned earlier. Then there was a little confusion, but this is what really we need. We said that if two vectors are parallel, the dot product is maximized, and if they're perpendicular, the dot product is 0. So that's what we used. Then we said if we have a vector and we consider all the points that when we draw a vector from the origin are perpendicular to that, what shape will be? And that was a line in 2D plane. And it turns out the line that goes through the origin is a subspace because linear combination of points on the line will be on the line, and it does include the origin. Then we talked about linear varieties, which is when we translate the line to a bunch of parallel lines. Those are all valid, but they're not going through the origin, so we call them affine subspace. As opposed to linear, linear fixes the origin. Then we showed that this is equivalent of what we learned previously, that the line has a slope and y-intercept. Okay, so today we are going to make it more interesting, and that's by talking about planes. So the extension of hyperplane from 2D, which is a line, to a 3D space will give us the ordinary plane. And plane is just a flat surface, and it has no end. It goes to the infinity. And you can imagine that it will cut the space into two half spaces. One is, let's say, to one side of the plane, the other one is the other side. So it's always like that. Okay. So we started with the idea that picking a vector and all the points that creates an orthogonal vector relative to that should give us an object in any space. We just follow the same idea. If this is my 3D space, again, we could talk about a line that goes, a vector that is fixed at the origin, but because we did it previously, we just talked about the general case. If I have a vector such as A, then I consider at a point x0. Now consider all the vectors that have dot products, all the points that if we create a vector relative to x0 will create 0 dot product with A. So A is dot product with x, any arbitrary point in the plane relative to x0 will be 0. Okay, so we know we can write this in this form. And the right-hand side is just the scalar, which we define it as d. So we learned that we could write it like this. A transpose x equals d. So d is a real number here. A and x are in 3D space. So A is a vector. It's called normal vector. So this is normal vector of the plane. Or in general, we have normal vector of the hyperplane later. And x is any point in 3D. I'm going to try to draw a plane. It's not very easy, but hopefully, okay, it's not too bad. But the plane is not limited to these lines. This is just for the sake of visualization. The plane can continue to the infinity. All right, so A transpose X means A1, X1 plus A2, X2 plus A3, X3 equals constant. And we can, just like line, we can say, for example, we can derive x3 in terms of x1 and x2. That will give us an equation that we can plot it in 3D. That's the regressor form. D is called, we will see why. D is called distance from the origin. So D is a scalar number that tells us how far we are from the origin. So maybe somebody can tell me, well, what is the meaning of this? We have a normal vector, we get the dot product of it with any point must give us D. What does a point that satisfies this equation look like? No answer? That's expected from an empty class? I give extra points. You have to set a reward. So the question is, what is a point that satisfies this plane equations here look like? Well, the answer is somewhat obvious. It must be on the plane, right? If this is the equation of the plane by the derivation that we had from the orthogonality of any vector we draw relative to point x must have 0 dot product, must be perpendicular to the normal vector, then any point that we choose, such as x, any point such as x that satisfies the plane equation lies on the plane. So we're talking about points that live on the plane. These are all the points that live on the plane. Now that's not the entire space. There's one half of it that is, let's say, in the upper side. I'm talking about this side. And there's another half that they are in this side. And you can see that the plane is cutting the space into two subspaces. Okay, so this is the plane equation. And now we're ready to generalize it to Rn. Okay. What was orthogonal to A? So the vector we're talking about here, right? The plane and vector A. A is orthogonal to the plane. Right, that's correct. Yeah? So we call it the normal vector of the plane. Which, by the way, means that if I give you a vector, a 3 vector, then this is a typical question in math books or practice questions. Given a vector, given a vector and a point, form a plane. So you immediately use, let's do it. Let's do an example. Given A equals 1, -2, 3, and x 0 equals to 0, 1, -1. Form a plane. And the answer will be, well, A is our normal vector. So we know that A dot product of A with x minus x0 must be 0. And we know that D equals A dot product of A with x0, which is 1 times 0 plus -2 times 1 plus 3 times -1. And that's -5, if it's correct. I'm not good at arithmetic anymore. People warned me when I was younger. Okay, so we have D, and well, we have our plane. It's 1x x1 minus 2 x2 plus 3 x3 equals -5. This is our plane. Now, your practice is that try to visualize it. See if you can figure out how to draw it in a 3D. Roughly, draw a coordinate system in 3D and see if you can draw it. And a hint is that if you can come up with 3 points, that satisfies this equation, that will help you to know where to draw the plane. And the alternative question could be, given 3 points, draw a plane, but for that we need cross product. That we should talk about it. That's also needed for the background of machine learning and computer vision. But for now, we don't talk about it. Maybe later we can solve that question. Okay, so now we're going to move on. This was plane. This is really what you should be comfortable with. They will probably review, but if you're comfortable with this, you'll have a quick start in any course related to computer vision and machine learning. Okay, is there any question? No? So now we're going to talk about hyperplane, which is generalization to Rn. Now, the nice thing about Euclidean space that we're working in is that when we talk about dot product, it doesn't matter if it's 2D, 3D, 4D, or 10D, or in n-dimensional. It is always correct, so it's already general. But we talked about the more special case because we can visualize 2D and 3D. It's not trivial to visualize in an understandable way for us higher dimensions. So we're going to just focus on a more abstract definition of it instead of visualization. And that's where a lot of notes start. I wanted to start from lower dimensions so you get comfortable how to imagine it. And then you should be able to relate this abstract definition to an imaginary plane. So a hyperplane is a set of points in Rn such that A transpose x minus x0 equals 0. So it is exactly the same definition. However, here we have A and x are n vectors. So x is a point, A is a vector, but they look the same for us. And also x0. Okay, if we expand this, we will get A1, x1, plus A2, x2, plus AN, xn. And again, A transpose x0, we will define it to be D. And D ends up being a scalar because it's the output of the dot product of two vectors, two n vectors, or vector and a point. So D is a real number. So this is a hyperplane. So it's important to generalize because a lot of problems when the input is not 2D or 3D can happen in practice, and those are not necessarily spatial. That means related to the 3D coordinates that we see in real world. And This way we can model them, okay? So a feature vector in machine learning, for example, it can be n vector, and that's an abstract space. For example, the way we can learn a feature about the face of a celebrity in a neural network, somewhere in the middle of the neural network, there is a vector space, maybe, let's say, 512-dimensional space. That's the feature vector. Now, we don't know what it means, but those are useful features to do tasks like classifications. Okay, so now we have our hyperplane, and hopefully you can relate it to the previous discussions. Do we have any questions? Okay, so we can move on to distance. The last thing in this topic is the formula for the distance of any point to the plane, or in generally hyperplane. Distance of a point to the hyperplane. Now, when we say distance to the hyperplane, that means that that includes distance to the line, distance to the plane. So you might have seen point to line, point to plane distance metrics. Well, we could generalize it, meaning this means if you have any point in the space here, this point here, if I want to know what's the distance of this point to the plane, there is a way for me to know it. And I'm going to redraw here. Here's our normal vector. Okay, we have now suppose we have a point such as y. What is the distance to the plane? Now the distance is the shortest line that will go through the plane from that point. Okay, and shortest means the line that is orthogonal to the plane. All right, so we know that. And how can we calculate that? So what are the tools we have? We know x0 is a point on the plane. That's how we get the right-hand side, d, right? And if I suppose I can draw a vector like this to the point. Now remember, the dot product of A and B means if this is B, this is A, the magnitude of dot product will project. So dot product means that if I considered B as a unit vector, means a unit vector along B is B divided by its norm. And that's the unit vector along B. This means if I give you any vector, you just want to use the direction. You don't want the magnitude. You want to get the direction in the space. You just normalize the vector, and that's the direction. It's intuitive because you don't want it to have magnitude. The norm must be 1. By normalizing, we know that's the direction, but we're not going to scale anything if we use the unit vector. So this is going to be our unit vector EB. So the dot product will project along that side, and A dot B EB, let's call it A prime. You remember a better notation? When we project a vector along another vector, did we have a better notation? I don't recall anything. We could call it C, any other vector, but let's call it A prime. Not the best choice of notation. Now A prime, so A dot B is the magnitude of vector A. It's the strength of vector A along vector B. In physics, we use that a lot because it has physical meaning for us. But it makes sense in Rn too. So A dot B is the magnitude, and we'll get A prime. Maybe I should. Okay. All right. Now the important, this was a side note. The important consequence of these facts from dot product is that if I take the dot product of A, my normal vector, with the vector y minus x0, I'm going to have my vector y minus x0 along my normal vector. Now that's perpendicular to the plane. I can work with that. And let's see what we get. A, the choice of colors are random, but I'm gradually coming up with a pattern. I started using black for the title. So don't expect consistency. And if you're wondering, there's a rule here. There is no rule. This is Wild, Wild West in this notebook. So we get A, it's dot product or transpose with y minus x0. And this will give us A transpose y minus A transpose x0. And now, this is not going to be 0. This is my question for you. I claim that this is not going to be 0, and you tell me why that's the case. You can't answer it. You really want to, but check the chat. So why is that what I wrote is not going to be 0? Exactly. That's very important. That is not 0 because y is not on the plane. But given what we know about dot product, that's the projection of a much longer distance, the vector that connects one point from the plane to, by the way, x0 is arbitrary because any point on the plane will satisfy the equation. So if you pick any point, that's fine. So x0 is really any point on the plane. So we get our vector y minus x0. Its dot product will make it perpendicular to the plane. We like that. Now if we know its magnitude, that sounds like to be the distance, right? However, if A is not a unit vector, if the magnitude of A is not 1, we can already guess that this is going to scale it. You might scale it twice, 3 times, whatever is the magnitude of A. So it's important to also normalize it with the magnitude of A to make sure. So A does not need to be a unit vector when you define the plane, but when we calculate the distance, we need to be mindful of that. So we arrive at the formula that, let's call it capital D, distance to the hyperplane. Now we're talking about distance. It could be signed distance if you do not take the absolute value like I'm going to do, because it matters if you on top of the plane or below the plane. You can get a signed distance. But let's make it just the magnitude. So the distance is A transpose. And remember, this is D. A transpose Y minus D divided by norm of A. And obviously, A must not be a vector of 0. We wouldn't have a plane to begin with. So this formula is assuming there is a plane, because if norm of A is 0, A is a vector of 0, there is no plane. So in practice, we write it like this, but in practice, you're not going to have any problem because there is a consistent plane to begin with. Okay, so we got our distance. Does this make sense to anybody? Everybody? This formula? But when you see that, you can start doing dot product in your brain that, oh, okay, A dot Y is making it orthogonal, right? And D is the distance from the origin. I'm going to subtract that because I want to know the distance relative to the plane, not the origin. So A dot Y minus D is the distance to the plane. Now I'm taking the absolute value to make it magnitude. It could be negative, depending on which side of the plane you are. And then I divide it by the norm of A to make sure I'm not scaling it, because then that's not going to be correct. Is this important in engineering, computer vision, machine learning? Good catch. So A not equal to 0. That's true. I can say that was intentional to see if people are following, but it was not. So some examples too. This is already important. We can guess that a lot of problems that you try to solve, maybe you want a metric, and you can use this. For example, LiDAR. Jesse showed you LiDAR. Those point clouds that we get from LiDAR, when we have one scan of LiDAR and then the sensor moves and we get the second scan of LiDAR, we actually use this metric, point-to-plane metric, to register 2 point clouds from 2 different time steps to find the transformation, rigid body transformation, that aligns two point clouds. And that's very common. It's a very important problem in robotics and 3D computer vision. We work on it a lot. And in fact, what you did in project 1, you were given the trajectory. That trajectory can come from an algorithm like that. So it is very useful. Now, when the signed version of it is useful. Now, in our example of the classification, we will use the signed version of it. So we don't take the absolute value. In computer vision, if you have a camera looking at a surface, it's important which side of surface you're looking at. In computer graphics, when they want to shade the surface, you want to shade it relative to the viewpoint. If you move the camera to the other side of the plane, for example, you want it to have different texture or visibility. In computer graphics, usually this viewpoint is very important. Okay? And then you hear some algorithms, viewpoint invariant. So they talk about some, for example, if you have a metric that tells you the viewpoint, the sign of, for example, this will determine the viewpoint, which side of the plane you are. Maybe you use that to come up with some rules that make your algorithm smarter. So it shows up in different places. Okay, we're done with hyperplanes. That's all you need to know to make money after taking machine learning and computer vision courses and knowing programming. Then you're ready to make money. Okay, we should talk about quadratic programming. So, do you have any questions for hyperplanes and distance? Was it clear? Because we want to move on. Okay, we can move on, and we have recitation and piazza if you want to continue the discussion for hyperplanes. Quadratic programming. You hear this a lot later in your life, if you stay at the university until the end of your degree and more. QP. So you hear people say, oh, that's just a QP. Say, what the hell is QP? It's quadratic programming. Most of the times, it's quadratic programming. And then they add more stuff, QP, QC. That first time you hear it, it will blow your mind, but it doesn't mean anything complicated. It's just the optimization problem with constraints, and that means constraints are also quadratic. So QP is a quadratic program. First time I read that, what is a program? It's got nothing to do with what I'm reading, and that's apparently true. Historically, program was used to define a mathematical optimization problem. It's unrelated. There's no point thinking about it more. There is no, I mean, we're used to it. It makes sense to us, but it didn't make sense for the first time. There's a piece of history that Richard Bellman came up with. I don't know if that's true. Came up with the program in dynamic programming, and because he was trying to hide what he was working on. people not realizing actually what it's doing. It sounded more sophisticated to sell it to people who were paying him. Now, I don't know if that's true, but that makes a lot of sense as well. So anyway, this is a coined term, quadratic program. Is like this. I'm going to insert a picture from the book. It's not in the middle. I have to move it one more time. It's a little disturbing. Okay, I'm good now. I don't have to think about it when I'm explaining it. So it's summarized in the book in the incomplete chapter about optimization, which we will complete it. So a quadratic program takes this form that you see. That 1/2 is completely for the beauty purpose. And when people differentiate, it gets canceled. So it's a constant, it doesn't matter. Q transpose, X transpose QX, that's called a quadratic form. And in general, a quadratic form can have that linear term plus small q times x. So the goal is that find x that minimizes the quadratic objective cost function. X is a vector in our M here. And in general, we have constraints. We have inequality constraints that we say A times, matrix A times X less than a vector B. We can have equality constraints. A times X equals B. And we can have lower bound and upper bound for each of the X values in the M vector that we have. So it's a search problem. We're trying to search for a decision variable X that minimizes our quadratic objective function. At the same time, it satisfies the constraints. A solution that minimizes the constraints, if it violates the constraints, it's not a feasible solution, okay? So we say a minimizer it's a weird term to write, minimizer. M-I-N-I-M-I. I was doubting myself how many more I should put. A minimizer of 1155, this equation here we see, our quadratic program, is called feasible. It's a feasible solution if it satisfies all constraints. Or you could say it does not violate any constraints. Okay, so that's an important fact. That makes sense, otherwise we would not put the constraint. If we don't care about a constraint, well, we don't put it in the problem. If we put it in the problem, we do want it to be satisfied. For example, you're trying to plan for minimizing cost of buying a bunch of stocks, right? You want to create a portfolio, and then you want to create your stocks, and you don't want to spend more than, let's say you don't want to spend more than $10,000 on Tesla. You want to buy some mutual funds, another $10,000, and then you want to buy Apple stock, $5,000, right? And then you have a bunch of other stocks that you want to make sure your portfolio is not too skewed. But you don't know how much of each you should buy. You just know the maximum and minimum you want to spend. Now maybe you come up with a quadratic cost, and you just try, you give it to computer, you solve it, and computer will tell you how much you should invest in each of the stocks, right? So it has, in economics and engineering, it has a lot of applications. In optimal control problem, we want to find the control actions. We use this problem. In your project 3, MPC, this is what we're doing. I have 2 minutes. By the way, that was not an advice for investment. Do not do that. You're going to lose your money. You should do something more advanced to make it risk averse. Okay, so 2 minutes. So our goal is to solve two examples. One is quadratic example 1. I'm going to add the picture for motivation because it's a very colorful photo, and you might get more motivated by looking at this. Okay, we want to very quickly, I'm just going to write the problem. We have a cost function, x1 and x2, and that equals x1 minus 2 squared plus x2 minus 1 squared. And our constraints are x1 plus 2x2. This is just a simple problem I came up with, toy example to practice. And we're not going to solve it. We just end this meeting with the problem statement. So I have all my constraints, and I have my cost function. You can already guess x1 equals 2 and x2 equals 1 is the solution. It's intentionally chosen to be like that. So the solution is 2 and 1. And these lines that the contour, the colorful contour you see, that's my cost function. Because I have two variables, I can visualize it. And the lines are my constraints. Think about it. See how it works. Follow the legends on the figure and tell us if the constraints are violated or not. Then we're going to continue to solve this, and then we formulate our classifier on Friday. And I'm going to show you quadratic programming code in Julia as well. We figured the solver. I think it works on IllumiDesk, so you should be able to try it. Thanks for joining us, and we're going to end the lecture now.